Hi everyone, welcome back to our course Manufacturing Processes. Today we are going to discuss about bulk deformation process. In bulk deformation process, we are going to discuss about a rolling process. The learning outcome is describe various metal forming processes such as rolling, forging, extrusion, drawing, and compute their process dynamics and performance. So bulk deformation already we studied in the previous lecture. What is a bulk deformation process? Metal forming operations which cause significant, massive change in shape and size. This process is called bulk deformation process, but there will not be any addition or removal of mass, but there will be a significant change in the shape. This is called bulk deformation process. The starting materials for bulk deformation process is cylindrical bars, billets, etc. So cylindrical bars and billets can be like rectangular or circular in shape. So these processes involve a compressive stress, normally compressive stress to produce plastic flow into the desired shape. This can be performed in cold condition or warm condition or in hot conditions. So in hot condition, if we increase the temperature above recrystallization temperature of the material and then we apply a compressive stress, the material will undergo significant deformation and there will be a new grain formation in the material in hot working condition. In cold working, what we do the operations under normal conditions, ambient conditions. Strength will be much higher in cold work products and finishing also will be very good. Little or no waste, and you can see here there will not be any wastage of material. We could be able to produce net shape or near net shape in such operations. So as you could see here in rolling process, we feed the material between two rollers as they rotate in opposite direction. What happens? The rollers will pull the material in one direction and it will come out from the other direction. So what happens is as the material is fed between the rollers, there is a compressive stress acting between the roller and the material and the specimen to be reshaped, and this compressive force compressive stress will induce a plastic deformation of the material, and the material will get deformed and we will get the final finished product. Now, what are the basic bulk deformation processes? The basic bulk deformation processes are rolling, forging, extrusion, and wire drawing. Rolling means we feed the slab or plate between the two rolls, and the plate or slabs will get squeezed, compressed, and we get the final product. Forging, the work is squeezed between the dies, and we get the final product. Extrusion, we squeeze the material through a die, through an opening, we force the material through an opening and we get a final finished product. Wire drawing, diameter of the wire or bar is reduced by pulling it through a die opening to produce wires and bars. So let us study about rolling process. It is one of the widely used method for producing slabs, sheets, roads, etc. So channels, I-beams, then L sections, etc. So deformation process in which work thickness is reduced by compressive stress exerted between the two opposing rolls. We have two opposing rolls, they rotate in opposite direction. When we feed the material between the rolls, the compressive stress will compress the material and the material will get squeezed, material will undergo, it will reach the plastic zone, material will undergo plastic deformation and its length increases, width decreases, and we get the final finished product in rolling. So the stress induced is compressive stress. It can be done either at cold condition or at hot condition. You could see different roles here. These are widely used in industries to produce several parts. Now the roles, rotating roles perform two main functions. These roles are used for inducing friction between the work part, and this will pull the work in the gap between them by friction. Simultaneously, it will skews the work to reduce its cross section. So it can be flat rolling. Flat rolling means used to reduce the thickness of a rectangular cross section. This is flat. So you will get rectangular cross section. Shape rolling means you will get square cross section is formed into a shape such as I-beam, etc. Channel beam, I-beam. So you will get a particular shape using shape rolling. Rectangular, you will get a flat rolling. Based on work temperature, you can have a hot rolling or cold rolling process. Hot rolling means this is normally the rolling process done at higher temperature, above recrystallization temperature. Significant deformation, massive deformation is possible. Cold rolling produces good surface finish and good accuracy, and strength also would be good in cold rolling process. As you could see here, these are the raw materials, incoming raw materials like bloom, slab, billets. These are the raw materials. They are converted into structural shapes like I-beams used for rails, plates and coils, billets, bars and rods, etc. These are the parts produced from a rolling mill. So roll materials, what are the roll materials which are used? The roll materials are produced by cast iron, hard materials, cast steel, forged steel, very strong materials, and even aluminum alloys can also be used. The incoming raw materials, as I explained, bloom, slab, and billet. Bloom is a square cross section, at least 6 inch. Billet is square cross section smaller than 6 inches, and slab is rectangular in shape. Slab in rectangular in shape, bloom more than 6 inch, and billet square section less than 6 inch. And bloom is used for producing sheets, billets used for rod and pipe, slab used for rails and I-beams. So as you could see here, parts produced by rolling, many parts, several parts, as you could see here. Plates more than thickness 6 millimeter. Structural applications, they can be widely used in ship hulls, boilers, bridges, machinery. So we can produce plates more than 6 mm, and we can produce sheets less than 6 mm, typically provided as coils or flat sheets. Large variety of applications where they are used, plates and sheets. You could see here truck frames, rail tracks, automobile clutch plates, wheels and wheel rims, pipes and tubes, water heaters, agriculture, many stampings, compressor shells, metal buildings, doors and shelves. Many places we can use the rolled parts. As you could see here, a flow diagram. This is the incoming material, slab, billet, and bloom. And bloom is square but more than 6 inch, slab rectangular, billet less than, bloom greater than 6 inch, and billet less than 6 inch. They are converted into coil. You can see here sheets like coils, rods, steel plates, bars, seamless tubes, pipes, round tubes. Look at that, how different roles are used to produce different shapes. See, eye shapes, channel shapes, several shapes, roads. How rolling mills are used to produce several shapes. You could see from this flow diagram. So starting from the sheets, plates, bars, rods, pipes, then structural elements like H beams, I beams, H beams, like that. So here, a diagram of a flat rolling. As you could see here, the mechanics of rolling process. The initial thickness of the material before rolling is T0. The final thickness of the material after rolling is TF. So what happens as rolls rotate in opposite direction, they skews the material by applying compressive stress. The material will undergo plastic deformation and its shape and size are changed. Now the mechanism says T0 is the incoming thickness, TF is the final. So T0 TF by rolling process. So P is the exerted, we can say compressive stress or the roll pressure exerted on the material. The pressure exerted on the material is P. R is the radius of the rolls. Theta is the contact angle. As you could see here, contact of the between material and the roller is from here to here. So this angle is theta, and the length of contact, we call it as contact length. You can see here the distance at which the roller is in contact with the material to be deformed. Initial velocity of the material is V naught and final velocity of the material is Vf. Initial and final velocities are also given. So here the draft is the amount of thickness reduction, as I explained before. Draft is the difference between initial thickness, starting thickness, and final thickness. So you are feeding T naught, you are getting Tf. So the difference is called a draft. So the reduction is expressed in terms of initial stock thickness. Reduction means the ratio of draft to initial stock thickness, d over T naught. Then we have other equations in here, as I explained before. The continuity volume flow rate, initial volume flow rate is equal to final volume flow rate. So T naught times W naught times velocity, initial velocity. So initial thickness times initial width times initial velocity is equal to final thickness times final width times final thickness times final width times final velocity. So this is the volume meter cube per second, meter cube per second. This initial volume flow rate in meter cube per second is equal to final volume flow rate of the material in meter cube per second. So slip. So if the velocity of the material and the roller are same, there is no slip. If they are different, there will be a slip. That slip is that means the roller will rotate without taking the material. That is called a slip. So slip is equal to V final velocity of the material minus velocity of the roller, linear velocity of the roller divided by linear velocity of the roller. So final velocity of the material minus initial or velocity of the roller divided by velocity of the roller. So rolling force, how much force is applied in here? Rolling force is stress times area. The stress is the flow stress YF times area is W times L. This is how we calculate the rolling force. Now the contact angle is equal to, if you take the angle theta here, L is the length or contact length, we could say. We can approximate it to contact length L. R is the radius. So using this, we can find theta equal to sine inverse L over R, and L, from this L is square root of R square minus R minus T naught minus Tf divided by 2 the whole square. This equation can be approximated as contact length. The length of contact between the roller and the workpiece or the specimen is square root of R, radius of the roller, times T naught initial thickness minus Tf final thickness. The strain, the deformation obtained by the working roll is calculated in terms of T naught and Tf, or initial thickness and final thickness. Strain is equal to log initial thickness divided by final thickness. Now the total stress or average stress induced in the roller, between the roller and the workpiece, is YF, which is equal to K epsilon raised to n divided by 1 plus n. K is a strength coefficient, epsilon is the strain, and n is a strain hardening coefficient. Using this equation, we can find the average flow stress required for the rolling operation. How much is the average required stress required for the rolling operation? That is equal to K epsilon raised to n over 1 plus n. Epsilon is the strain value. Flat rolling terminology, as we can see here, this is having non-uniform grains, as you could see here. When we heat it, the grains, the above recrystallization temperature, and when we roll it, new grains will be formed and developed in here. Recrystallization will take place, so material will have new grain structure after a hot rolling process. So the wrought product with the small uniform grains will be produced, and before rolling you could see here ingot with non-uniform grains. So the basic principle in flat rolling process is the friction between the roller and the workpiece. Greater the friction force, there will not be any slip. Lesser the friction, there will be a slip between the roller and the workpiece. It is a friction between the work and the roller that drives the workflow between the rolls. The friction force is developed because of the coefficient of friction and the compression or compressive force between the roller and the workpiece. Now we can see here a graph of pressure, roll pressure versus the distance L, contact length L, entrance to exit. As it moves from entrance to exit, as you could see, the roll pressure increases, reaches to a maximum, and towards the exit it decreases. This is how the pressure, roll pressure varies with length from entrance to exit. So the rolling process is governed by frictional force and the rollers between the rollers and the workpiece. The frictional force at the entrance side is higher than the exit side. This allows the roller to pull the workpiece towards the exit end, and the force, average force required for rolling is equal to flow stress times area W times L. WL is called roll work contact area. So the flat rolling terminology, we can calculate the maximum draft. In rolling, there is a limit. How much we can reduce? Can we reduce to any amount? How much draft we can produce? Say we can reduce from 100 mm to 10 mm. How much thickness we can reduce by rolling? So the maximum thickness we can reduce by rolling process, Dmax, maximum draft, is mu square R. Mu square times R. Mu is the coefficient of friction and R is the radius of the roll. So Dmax is equal to mu square R. Mu is the frictional coefficient and R is the radius. As you could see here, friction causes rolling. If mu is 0, friction will be 0. Then if there is no friction, mu will be 0. Mu 0 means draft becomes 0. That means there is no rolling takes place. Whenever there is no friction, no draft, no rolling. So this is all about about part 1. We have a simple exercise here. So the torque of the roll can be estimated as how we can calculate torque of a rolling mill. Torque is calculated by the equation 0.5 F times L. F is the rolling force and L is the contact length. This is how we calculate torque produced by the rollers, and the power used to drive the roll. Power used to drive the roll, P equal to 2 pi NFL. N is the rotational speed, F is the rolling force, and L is the contact length. So the torque and power, torque is 0.5 FL and P is the power 2 pi NFL, N is the speed RPM, F is the force in Newton, L is the contact length in meter. We can calculate how much torque and power required for rolling operation. For example, if we want to reduce a material from a thickness 50 to say 40 mm, 50 mm to 40 mm, these are the dimensions of the material. How much torque and power required to convert this material from 50 mm to 40 mm, that can be determined using the torque and power equations. Thank you very much for listening part 1 material. We'll continue with part 2 in next video. Thank you.